Welcome to the deep dive. We're here to get into the nitty-gritty of the sources shaping our tech world. Today, we're tackling something pretty big in AI, a major reality check for those AI coding agents everyone's talking about.
Yeah, it's a fascinating moment, actually.
Definitely. I mean, you've probably seen the headlines. I know I have. Models like GPT, like Claude, they were posting these, frankly, amazing scores, sometimes over 70, even 80% on benchmarks like SWE-Bench verified.
Right, those older tests. And it really looked like, fully automated coding was just around the corner.
Exactly. But then, well, then came SWE-Bench Pro, a new, much tougher exam. And bam, the scores just tanked. We're talking the best models suddenly stalling out around, what, 23% success?
23% from over 70 down to 23. That's a huge drop.
It is. It's sobering, but maybe necessary. It means even the smartest AI coding tools are failing on realistic tasks, like 3/4 of the time.
Wow. Okay. So this isn't about saying AI coding is a failure then. No, not at all. It's more like a recalibration, a much needed one. SWE-Bench Pro is designed to be hard to reflect the kind of challenges professional developers face. So our mission today really is to unpack what makes this test so different, so much harder, and what that pretty low 23% score actually tells us about where AI stands right now with coding.
Okay, let's get into it. Why the need for this hard reset? If the old scores look so good, why throw them out? What was fundamentally wrong with getting a 70%?
Well, that 70%, while sounding great, was masking a couple of serious underlying problems. Two main things, really. First, you had what's called benchmark saturation. The old tests, like the original SWE bench, they'd just been around too long. They were solved, in a way.
Like teaching to the test.
Precisely. When a benchmark saturates, it stops being a good measure of actual capability. It can't distinguish between genuine intelligence and just being really, really good at that specific test. Models look great on paper, but the really hard problems, still unsolved.
Okay, so the test got too easy or too familiar. Makes sense. What was the second flaw? You said it was deeper.
Yeah, this is the big one. AI benchmark contamination. This is something the field's been wrestling with, maybe sometimes quietly. Think about how these models are trained. They crawl massive amounts of data from the web, right? Including tons of code from places like GitHub, public issue trackers.
Right, all that open source code.
Exactly. And because of permissive licenses and just the sheer volume of public code, there's basically a direct pipeline from those code repositories right into the model's training data.
I think I see where this is going. So the model might have already seen the test questions or something very close to them during its training.
You got it. It's essentially remembering the answer, not figuring it out. It looks smart, like it's well-read in code, but it's demonstrating recall, not real problem-solving skills. It's like giving a student an exam where they've already seen the answer key.
Okay, that feels like cheating, or at least not a fair test of reasoning.
It fundamentally undermines the test's validity. So SWE-Bench Pro was built from the ground up to specifically break that cycle, to stop the contamination and force the AI to actually reason about problems it genuinely hasn't encountered before. It's about restoring trust in the scores.
That makes a ton of sense. You need a test the models can't study for, basically.
Mm-hmm.
So let's peek inside SWE-Bench Pro. What makes it so much harder? How does it actually mirror what, a professional software engineer does day to day? You mentioned 3 key ways.
Yeah, they're really focused on realism. The first big difference is what they call enterprise-level difficulty. Forget small, isolated functions. This benchmark makes the AI agents fix real bugs within entire complex code repositories.
Full repositories, not just like a single file.
Nope, full repos. The kind of environments where a change in one place can break something totally unexpected somewhere else. We're talking production-level complexity.
And the fixes themselves are more involved too, right? I read something about the average fix size.
That's right. The median fix, the typical solution needed, involves over 100 lines of code. And often, that code needs to touch multiple files.
100 lines, multiple files, wow.
Yeah, it's not just fixing a typo. This forces the AI into much more sophisticated behaviors. Long horizon planning, thinking several steps ahead, navigating complex code bases, using tools like compilers and linters correctly, and making edits across different files that all work together, compile, and pass the existing tests.
That sounds incredibly challenging compared to, say, writing one function in isolation. It's about the whole system.
Exactly. It's systems thinking. It's understanding how changing file A impacts the logic in file C, and that integration, that synthesis, seems to be where current models really struggle.
Okay, the enterprise complexity makes sense. Now, how did they tackle that contamination problem we talked about? If some code is public, how do you stop models from just memorizing it?
They used a clever two-pronged approach involving licenses and private data. So for the public part of the benchmark, they deliberately chose repositories that use strong copyleft licenses, like the GPL.
Ah, the general public license. That has implications for commercial use, right?
It does. It makes it legally and practically much harder for companies building closed-source proprietary AI models to just hoover up that code and stick it directly into their training sets without potentially open-sourcing their own model improvements. It creates friction against easy absorption.
Okay, so that discourages training on the public test data. What about the other prong?
They also build a significant commercial portion of the benchmark. This uses code bases from private startups they partnered with. This code is proprietary. It has almost zero chance of ever having appeared in a public web crawl or data set.
So it's truly unseen data for the models.
Almost certainly. And crucially, they also keep a chunk of the benchmark, a held-out set, completely private. They use this to continuously check if models start overfitting to the publicly known parts of SWE-Bench Pro over time. It's like having a secret umpire keeping the game fair.
That's smart. Keeps the benchmark relevant and resistant to being gamed down the line. Okay, complexity, contamination, resistance. What was the third element making it a better test? Something about fairness.
Yes, human-centered verification and unified evaluation. This addresses the concern. Are the AIs failing because the task is hard, or because the instructions were just bad or ambiguous?
Right. Like maybe the bug report wasn't clear.
Exactly. So for every single problem in SWE-Bench Pro, a human has refined it. They provide a really clear problem statement, explicit requirements for the fix, and define the interfaces the code needs to interact with. This reduces the ambiguity. It shifts the challenge away from trying to guess what the user wants, like a scavenger hunt for context, and focuses it squarely on implementation. Can the AI actually write the correct code to meet these clear requirements?
Got it. So it tests execution ability, not mind reading.
Precisely. And then, to ensure a level playing field, they run all the models under the exact same conditions. They use a standardized framework called SWE-Agent, give them the same base prompt, enable the same tools, and set the same limits on how many attempts or interactions they get.
So apples to apples comparison. No weird lab setups skewing the results for one model versus another.
Exactly. It makes the results much more reliable and reproducible.
All right, so we have this carefully designed, tough, fair benchmark. Now, the moment of truth. The scores. You said they were low.
Brutally low, honestly. Let's start with the public set results. This was based on 731 different issues drawn from those open-source, copylefted repositories. OpenAI's latest, GPT-5, managed to solve 23.3% of them.
Okay, 23.3. So just under 1 in 4. That's the leader.
That's the leader, yeah. Claude Opus 4.1 from Anthropic was right on its heels at 22.7%. So the absolute best models are basically hovering around that same low ceiling.
Wow. And what about other models? You hear about GPT-4o and various open source efforts. How did they stack up?
It's a huge drop-off, a massive gap. OpenAI's GPT-4o, which is generally considered very capable, only solved 4.9% of the issues.
Less than 5%.
Less than 5%. And a strong open source model like QWE-N332B, just 3.4%. So the difference between the top two and the rest is, it's vast.
That's quite a spread. Okay, so that's the public, potentially somewhat familiar despite licenses code. What happened when they hit the truly private, never-seen-before code in the commercial set?
Things got even tougher, which kind of validates the idea that unseen proprietary code is harder. On that commercial set, this was 276 issues. The scores dipped further. Interestingly, Claude Opus 4.1 actually edged out GPT-5 here, scoring 17.8%.
Okay.
And GPT-5 slipped a bit to 14.9%.
So best case scenario on completely unseen private code is less than 18% success.
That's about right.
So putting it all together, whether it's public or private code, the absolute best AI coding agents right now are failing on these realistic tests. What's somewhere between 77% and 85% of the time on their first try anyway?
Yeah, that's the pass it one metric they use. Does it get it right on the first generated attempt? And the answer is overwhelmingly no. More than 3 out of 4 times, even for the very best models, the first answer is wrong.
That's sobering, as you said. How does that compare to, well, us, humans?
Yeah.
What's the baseline?
That's a crucial point the source material makes. these issues in the benchmark. They were originally found and fixed by human developers working in those actual repositories. So the human baseline, given enough time and effort, is effectively 100%. We know these problems are solvable by people in the real world.
Right, okay. So the 100% isn't saying a human gets it right instantly, first try, under pressure.
No, no, it's not about speed or first-pass success for humans. It's just establishing the ground truth.
Yeah.
These are solvable problems within the context of the repository. The fact that humans did solve them proves possibility.
Gotcha. So the AI isn't just slow, it's often failing to reach the possibility threshold that humans demonstrate. The capability gap is just huge.
It really highlights the difference. You simply couldn't deploy an agent that fails 77% of the time to fix bugs in your production environment. The risk would be immense.
Oh, kidding. Okay, so this tough benchmark gives us a clearer, maybe harsher picture, but the framing is that this isn't a failure, it's a map. How does knowing why they fail help chart a course forward?
Because it changes the incentives for builders. You can't just throw more data at the problem or tweak prompts endlessly and expect big gains on SWE-Bench Pro. It forces a focus on improving the core reasoning and planning abilities of the AI. Improving your score on this benchmark likely means you've genuinely made the agent better at systems thinking, at handling complexity, at using tools more intelligently. It demands progress in areas like better memory, better internal planning, understanding code types, and creating tighter feedback loops between coding, compiling, and testing.
So it pushes development in a more meaningful direction. And do we know what kinds of failures are most common? Like when they fail, what does it look like?
Yeah, the researchers did analyze the failure modes, and they saw different patterns depending on the model's capability. For the big guys, GPT-5, Claude, the failures were often more subtle, more sophisticated. Things like semantic misses, understanding the syntax but getting the underlying logic or intent wrong, or algorithmic slips, choosing the wrong approach to solve the problem. They might also make edits across several files, but the changes don't quite connect properly to achieve the goal. They miss the full synthesis.
Okay, so higher level reasoning errors for the top models. What about the others, the ones scoring much lower?
For the smaller or lower tier models, the failures were often much more fundamental. Things you might expect, like basic syntax breaks, the code just doesn't compile, persistent formatting errors. They also saw really brittle tool use, like the AI tries to use the compiler or a linter but messes it up, gets stuck, or misinterprets the output. And a big one was context overflow. They just couldn't handle the sheer amount of information across multiple files needed to understand the problem. They got lost.
Interesting. So the failure modes themselves provide clues about the specific weaknesses at different capability levels.
Exactly. It gives builders concrete targets. If your model fails with syntax errors, you work on basic code generation. If it fails on semantic logic, you need to improve its deeper reasoning.
So if you're building these AI agents, SWE-Bench Pro isn't just a grade, it's like a diagnostic report.
Yeah.
What are the key takeaways, the practical steps builders should focus on now to push past this 23% barrier? The sources mentioned 4 key things.
Yeah, they distilled it down nicely. It really boils down to treating the code base less like a flat text file and more like a dynamic, interconnected system. First, treat repos as living systems. This means building retrieval mechanisms that focus on understanding interfaces between components, class invariants, function signatures, not just blindly reading thousands of lines of code. Index smarter, basically. Help the model know what context is critical.
Okay, smarter retrieval, not just bigger context windows. Makes sense. What's next? Tools.
Tools are critical. Second, lean into tool use, but with guardrails. The AI needs to use compilers, testers, linters constantly, but these loops need to be fast, reliable, and this is key visible to the AI's planning module. The agent needs to see, I compiled, it failed, here's the error, and use that immediately to adjust its plan, not just as a final check after writing 100 lines. Short, tight feedback loops.
Integrate testing into the process, not just the end. Got it.
Third, prefer surgical diffs. When the AI generates code changes, it should aim for minimalism. Generate patches or diffs that are small, targeted, easily testable, and ideally reversible. Even if the fix requires touching multiple files, the changes in each file should be as concise as possible. Change only what's necessary. This reduces complexity and risk.
Less is more, basically. Avoid sprawling, hard to understand changes. And the last one, about learning from mistakes.
Right. Fourth, diagnose failures with structure. Don't just log task failed. Classify the failure. Was it a syntax error? Context overflow? Wrong algorithm? Did it misunderstand the requirements? By categorizing failures systematically, engineers can work on fixing the class of problem, example, improve handling of type errors, rather than just patching one specific instance. That's how you get generalization, which is crucial for beating a contamination-resistant benchmark like this.
Okay, those 4 steps, smarter indexing, tight tool loops, surgical edits, and structured failure analysis sound like a solid roadmap.
It's a demanding one, but it targets the core challenges revealed by the benchmark.
So wrapping this up, this whole deep dive really underscores a shift, doesn't it? Away from flashy, maybe synthetic demos towards the hard, messy reality of real-world software development. That low 23% score isn't necessarily bad news. It's just honest news.
I think that's exactly right. SWE-Bench Pro, because it's contamination resistant, focuses on long horizon tasks, and is verified by humans, gives us the most reliable mirror we have right now for professional software engineering complexity. It forces the field to think about the whole system. The AI model, yes, but also the editor it uses, the speed of the build test cycle, the quality of the context it gets.
The score is a baseline, not a final verdict.
Precisely. It's ground zero for genuine progress. And the sources pointed towards an interesting blend of philosophies needed. Combining the Carpathy mindset, focusing on those clear, iterative feedback loops, the engineering discipline, with the Chollet mindset, which emphasizes the importance of abstraction, representation, and building truly intelligent, generalizable systems.
Right. Which brings us to a final thought for you, the listener, to ponder. We've heard that even the best AI agents today often fail on the semantic and algorithmic challenges. They get the syntax right, but miss the deep logic or the right overall approach.
The meaning behind the code.
Exactly. So thinking about those 2 core aspects of intelligence, Chollet talks about abstraction, defining problems broadly, and representation, structuring knowledge effectively. Which of these critical human capabilities do you think the next generation of AI coding agents needs to master most urgently? Which one holds the key to bridging that enormous gap we see today, from struggling at 23% all the way up to that 100% human baseline of possibility? Something to think about.
Definitely food for thought.
We'll leave you with that. See you next time on The Deep Dive.